If anyone has any questions, feel free to submit them in the question box, and we will answer them at the end of today's presentation. Joel, go ahead and take over.
Awesome. Thanks, Eva. Welcome to Packet Analysis with IEPA and AirPCAP NX. In this webinar, we'll introduce you to packet analysis with this really easy-to-use and visual packet analysis tool. And we'll talk about some of the ways that you can use that to troubleshoot and deploy really good, really effective wireless networks. Like Eva said, at the end of the webinar, we'll have some time for question and answer. So if you have any questions, feel free to ask those using the question tool, and we'll answer those at the conclusion of the webinar. My name is Joel, and I take care of all the training functions here at MetaGeek. I do things like teach webinars like these. Sometimes it's for us directly. Sometimes it's for our great resellers like Microcom. I also write knowledge-based articles, create training materials, and sometimes I even get to go and train our customers in person, which is really fun. If you're interested in getting involved with the wireless community, I highly recommend getting on Twitter. Twitter is an awesome place to kind of get involved with what's happening in Wi-Fi and to keep up on latest trends and learn new things. It's where I've honestly learned a lot of what I know about Wi-Fi, and so I just highly recommend getting involved with that if you can. So with that, let's go ahead and get started. The first thing that we need to think about when we're working with packet analysis is the half-duplex nature of Wi-Fi. Now, we're all familiar with an Ethernet cable, and with Ethernet, we have multiple twisted pairs of copper inside one cable, and that allows us to send traffic in two directions at the same time on one Ethernet cable. Wi-Fi is a little bit different, though. Instead of being full duplex like Ethernet is, Wi-Fi is half duplex, which means only one side can talk at a time. The end result of that is that only one Wi-Fi device can talk on any channel at any time. If two devices try to talk to each other, they'll basically just cancel each other out, and they won't be able to understand each other, much like you're familiar with a human conversation. So we have to think about this when we're working with Wi-Fi. So what does a wireless conversation typically look like? We'll delve into this a lot deeper later in the packet analysis webinar, but what we have to think about with this is how devices send data and how they acknowledge that data. The first thing that happens is, let's say that we have an access point that needs to transmit some data to another device on the same channel. The first thing that's going to happen is that access point is going to listen to that channel to see if anybody else is talking. It's going to do a clear channel assessment to see if everyone or if anything is talking on that channel. And then when it gets a chance, it'll transmit that data to the device on the other side. Now, in this case, let's say that there's a laptop and the laptop receives the data. The laptop is going to check that data to make sure that it understood it, and then it's going to reply with an ACK, or an acknowledgement. We just call it an ACK for short. Now, there's a few things that can go wrong here. Let's say that the data gets transmitted, but halfway through, maybe something else starts talking on the same channel and interrupts that conversation and garbles up that data. Or maybe the laptop is just too far away, and so by the time the data gets to the laptop, it's just too garbled up for the laptop to understand. In that case, the laptop won't understand the data, so it's not going to understand that data, and it's not going to send an acknowledgement. And what happens next is that access point is going to start wondering, okay, well, I never heard the acknowledgement from the laptop, so the laptop must not have received the data. So then the access point is going to transmit that data again. It's going to keep retransmitting that data until finally the data makes it through to the laptop, and the laptop can go, yep, check, I understood that data, and it can reply with an acknowledgement. So Wi-Fi is this constant process of sending data and receiving an acknowledgement. The big thing to remember is that on any given channel at any given time, only one device can talk. Now, we also have to think about kind of the differences between 2.4 and 5 gigahertz. We're not going to go really in depth with this here, not for this packet analysis webinar. But the big thing that I want you to understand about the differences between the 2.4 and the 5 gigahertz frequency bands is that in 2.4 we only have 3 non-overlapping channels to work with. Whereas in the 5 gigahertz band, we have 24 non-overlapping channels to work with. On each channel, we can only have one device talking at a time, and the result of that is that each channel has a limited amount of throughput, a limited amount of capacity per channel. The 2.4 gigahertz band is so much smaller than the 5 gigahertz band that we just don't have a lot of room for a lot of capacity, whereas in the 5 gigahertz band, we've got a lot more channels, so there's a lot more potential for a lot more throughput. Because when we have multiple devices on the same channel at a time, only one device can talk on a channel at once. For example, if we've got a channel here, we've got an access point, a bunch of client devices that are all on the same channel, if we've got an Android phone that is currently transmitting something to the access point, All the other devices on the channel have to be quiet and wait for their turn to talk. Only one device can talk on a channel at a time. And the more and more devices you put on a channel, the smaller and smaller and smaller everyone's transmit opportunities get. It's kind of like a dinner table. If you've got a dinner table with 4 people at the table, everybody's going to get a reasonable amount of time to be able to participate in the conversation and say what they want to say. Whereas if you've got a dinner table with 10 people at the table, well, then it gets kind of hard for everybody to get to say what they want to say because there's lots of people participating in the conversation. It's the exact same way with Wi-Fi. So we've got to watch out for that. We also have to think about what data rates are in use as well. In Wi-Fi, we're constantly switching what data rate we're transmitting data at. Now remember, this isn't our actual throughput. There's a lot of management overhead, as you'll see later in this webinar. There's a lot of things that happen behind the scenes, and so just because we have a data rate of 54 megabits per second doesn't mean that we're going to hit an actual throughput of 54 megabits per second. But devices are going to be constantly switching around data rates. It's called dynamic rate selection. They're going to be constantly picking which data rates they want to use. And so let's say that we've got a phone that's pretty close to the access point. It's not very far away. It can hear the access point really well. The access point can hear the phone really well. And so they're going to be able to maintain a nice, fast conversation, like maybe 54 megabits per second. Whereas out here on the very, very edge of the coverage cell, we've got another phone that can just barely hear the access point, and the access point can barely hear it. And because they're far away from each other, they've had to slow down their conversation so that they can enunciate better, so that they can make sure that each of them can hear each other just fine. So they've had to slow all the way down to 1 megabit per second. And when that happens, this device is going to take 54 times longer to transmit the same amount of data as this device. Slow devices consume more time on the channel. They take longer to say what they need to say. I like to liken this to the slow guy in the back of the classroom. Does anybody know what I'm talking about? You've all probably been to a classroom or something like that where there's somebody in the back where they keep raising their hand and they just ask questions very, very slowly. It takes them a long time to ask their question. And when they do that, the entire class has to stop, and they have to stop learning and listen to that person ask a very, very slow question. So we've all been there. We all know about the slow kid in the back of the classroom. That's kind of what this 1 megabit per second device is. It's the slow kid in the back of the classroom. It's the slow device on the channel. It's going to consume more time than devices that talk faster. Now, there's 3 different types of interference in Wi-Fi. The one that we're going to talk the most about today is co-channel interference. Co-channel interference occurs when we have a lot of access points and a lot of client devices all sharing the same channel. They're going to compete for time to talk. Whereas adjacent channel interference occurs when we have networks that are on partially overlapping channels. Like maybe we've got a network on channel 4, and we've got another network on channel 5, and another network on channel 6. When networks are on partially overlapping channels, instead of politely taking turns, they're just going to yell and scream over each other. They're going to just interrupt each other constantly, and so it's not going to be a nice, fast, and efficient conversation. Now, you may have noticed earlier when I showed you the channels in the 2.4 gigahertz band, I only showed you channels 1, 6, and 11. That's because those are the 3 channels that don't overlap, whereas all the other channels in the 2.4 gigahertz band, like for example, channel 4, channel 5, and channel 6, they all partially overlap with each other and they all cause adjacent channel interference. If everybody everywhere always used channels 1, 6, and 11 exclusively, we could eliminate adjacent channel interference entirely, and the 2.4 gigahertz band would work a lot better for everyone. Now remember, in the 5 gigahertz band, the channels don't partially overlap, so we don't have adjacent channel interference in 5 gigahertz band. It just doesn't exist there. We also have to think about non-Wi-Fi interference as well. The 2.4 and the 5 gigahertz bands, but mostly the 2.4 gigahertz bands, are the home of lots and lots of wireless consumer electronics. Think things like baby monitors, cordless phones, wireless video cameras, microwave ovens. The problem with those devices is that they will just jump onto a channel and start spewing the equivalent of garbage out onto the channel. And when that happens, any Wi-Fi devices on that same channel will basically just back off and be quiet and wait for their turn to talk. Non-802.11 devices, that means non-Wi-Fi devices, also need time to talk. They need to be able to get on the air and say what they need to say. And so we've got to think about that as well. Now, packet analysis is best for co-channel interference. With a packet analysis tool, we can capture an entire conversation on a specific channel, and we can see all the activity from the laptops and the tablets and the smartphones and all the access points. Packet analysis shows us the details about 802.11. That means Wi-Fi congestion on a specific channel, so we can see in depth what is going on a specific channel. But me, I like to start with the physical layer, which means I like to start by looking at the raw radio frequency activity in the spectrum. And you can do that with a spectrum analyzer like a Wi-Spy. And with a Wi-Spy, if you find a problem in the spectrum, you're going to see one of two things. First off, you might see a non-Wi-Fi signature like this cordless phone. This is a 2.4 gigahertz cordless phone, and since channel 11 is located about here, it's going to cause severe amounts of interference for everything on channel 11. And if you see something like that, that's when you're going to use spectrum analysis. That means something like a Wi-Spy and channelizer to identify and remove non-Wi-Fi interference. You're going to figure out what that interference is, and you're going to go track it down and just get rid of it, because it's just going to cause interference for any of your Wi-Fi devices, and it's going to cause extreme problems. Whereas if you look at the spectrum, and instead of seeing a non-Wi-Fi signature, if instead you see a Wi-Fi signature causing heavy utilization that's constantly using the channel, like this signature right here, then that's when we know, okay, so there's something going on from a Wi-Fi standpoint here, and that's when you're going to use packet analysis to dig deeper into that Wi-Fi congestion to find out what exactly is happening on this channel, what's going on here, and that's where packet analysis is really awesome. So you're going to make that jump from spectrum analysis, looking at the physical layer, to packet analysis, looking at the packet layer, looking at layer 2. There's a big difference between spectrum analysis and packet analysis. With spectrum analysis, that shows us utilization on each channel. Utilization basically is the sum of all the radio activity on the channel. It's the sum of all of the raw radio frequency activity on that channel. Think of it as looking at the raw radio waves. Whereas with layer 2, with packet analysis, instead of looking at how often the channel is being used from a utilization standpoint, with packet analysis, we're going to look at how often the channel is being used from an airtime standpoint. How much time are all of these packets and all of these conversations taking on each channel? Packet analysis shows us the details about the 802.11 congestion on the channel. So think of it kind of like this. Instead of looking at raw radio frequency activity, now we're actually looking at the packets that are flying around between all the wireless devices on each channel, so we can actually look at those conversations. That's what layer 2 is. So let's take a look at some of the different types of packets that you will see in Wi-Fi. There's 3 main types. There's management frames, control frames, and data frames. And we're going to go through and take a look at each one of those different types of frames before we jump into a live demo with IPA. The first type of frame is a management frame. And I hate to read directly off my slides, but this is really what they are. Management frames manage stations joining and leaving wireless networks. Now, some examples of different types of management frames are beacons. A beacon is simply an access point's announcement of its existence. When you get your iPhone out of your pocket and you look at all the networks that you can connect to, it's showing you that because of beacons. So, for example, my access point at home is right now doing this. It's sitting there going, hey, I'm Joel's network. I'm here. I support these data rates. I support this type of security encryption. You can connect to me. And it just repeats itself over and over and over again to let devices know that it's there. The next is a probe. A probe is kind of the opposite of a beacon. If I've connected to a network before, like maybe Joel's network, my phone is continually looking for Joel's network. It says, hey, Joel's network, are you there? Hey, MetaGeek, are you there? And it'll just continually probe for familiar networks. And if it sees, if there is a familiar network there, then you know, my network at home will reply with a probe response and say, yes, I'm Joel's network. I'm here. And that helps us get connected faster. And then there's authentication and association frames. These frames get exchanged when we actually join a wireless network. And it's just part of the nuts and bolts of how devices devices join and leave those networks. The next type of frame is a control frame. Control frames do just that. They control the radio frequency medium, and they make sure that other types of frames get delivered. Now, you remember the acknowledgements, and ACK for short. We go data, acknowledgement, data, acknowledgement. You remember that. The next type of frame is a block acknowledgement. Now, instead of acknowledging one data frame at a time, we can acknowledge a lot of data frames at a time. We can go data, 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 acknowledgement. So we can acknowledge lots of data frames all at the same time, and that saves us time on the channel. And then there's request to send and clear to send. We use these types of frames when we have trouble with devices talking over each other, like maybe if there's an access point that can see two client devices, but the client devices can't hear each other. We might implement request to send and clear to send to make sure that we let everybody on the channel know, hey guys, we're having a conversation right now. And so that's what RTS, CTS, or request to send and clear to send. The final frame type is a data frame. Data frames carry higher level protocol data. These are the whole reason why we have wireless networks. There's normal data frames. There's quality of service data frames, which we use to prioritize certain types of frames. Like right now, we're doing voice over IP to give this webinar. These frames, if I was giving this on a wireless network, these frames would be prioritized higher than other frames. And then there's null data frames. Those are for things like power save poles. They're not really data frames. There just wasn't anywhere else to put them, and so they ended up in that category. Now, traditionally, the way of doing packet analysis is one of those tools out there is called Wireshark. This is a free and open source tool, and this is actually a really great tool. We love Wireshark. The community put this together. The community supports it. It's an amazing tool, and it's a very, very powerful tool. But the problem with Wireshark is it's difficult to visualize airtime usage because you basically just get a bunch of packets in this kind of linear format as time goes on. And it's really hard to see who was talking to who and who was repeating themselves, who was talking slowly, and what exactly is going on the channel. And so we came up with a tool to complement Wireshark. We came up with a tool called IPA. IPA stands for I Packet Analysis, and it shows us who talked fast and who talked slow in these multi-layered pie charts. The pie charts show information in layers. So what we can do with this tool is we can take a packet capture, and then the tool will show us what happened on the channel during the packet capture. And it shows us with this pie chart who spent the most time talking. And the pie charts are presented in multiple layers. So let's take a look at all these different layers. The innermost layer shows us the individual network. Now, when I took this screenshot, I had my mouse hovered over the pie chart, so we get this nice little pop-up here. And we can see that there's a network here called Bronco Guest that used about 2/3 of the total amount of airtime on that channel. It used up about 2/3 of the time. So the innermost ring shows us the network. And remember, a network can be composed of multiple access points. The next ring out shows all the access points that are part of that network. So there's one access point right there, and there's another access point here as well. So we've got actually two separate access points that are part of this network that took up airtime on this channel. The next layer out is the individual client devices. How much time did the clients take up? This particular client took up a little bit more than 1/4 of the airtime, and then we have a few other clients here that didn't take up as much airtime at all. They took little slivers of airtime as time goes on. And then the outermost ring shows us the frame type, whether it's a management frame or a control frame or a data frame. And we color all those frames so you can see what is management overhead and what is actual data that's going to get sent over to the Ethernet side of the network. The orange ones are those control frames we talked about, the purple ones are management frames, and the blue ones are data frames. So we can see in this conversation right here, we spent most of our time sending actual data and a little bit of our time sending management overhead. You can see how just because we're saying we're connected at 54 megabits per second, we don't get all of that because some of that is management overhead. So with that, let's go ahead and do an IPA demo now. With IPA, we can do things like identify top talkers. We can identify devices that are having slow and inefficient conversations, and we can see which devices are transmitting the most data. We can identify problem devices as well. We can pinpoint slow conversations that consume airtime, and we can point out like those devices that repeat themselves. Those are problem devices. We can also get expert tips. IPA has a powerful expert tip engine in it, which automatically shows us client devices that have excessive retry rates, ones that are repeating themselves constantly, and we can identify network settings that can hurt performance. You can also export to Wireshark. IEPA has amazing, easy-to-use, and powerful filtering tools that you can use, and then you can export that data to Wireshark for deeper analysis. So with that, let's go ahead and switch over. Now I'm going to give you a quick demonstration of what it looks like to take a packet capture in IEPA, and then we're going to take a look at some sample packet captures that are included. So I'm just going to take a packet capture here on channel 6. I've got an AirPCAP NX, that's a product by Riverbed that we support directly within IEPA, and I have started capturing the entire conversation on the channel. Now you can see that we've already captured about 1.5 megabytes of data. We've captured about 4,000, almost 5,000 packets now. You can see lots and lots of packets fly through the air very, very quickly. So that's a pretty short packet capture, but let's go ahead and stop it. And IEPA is going to calculate out who spent the most time talking and who did what as soon as we open up that packet capture. So just as some quick things we can see that there's a network here called KBPH, which used up the most amount of time on the channel. It had 22 client devices connected to it, and that network had a total retry rate of only 9%. So that's pretty good. If we go one more layer in, we can see the specific access point that's part of that network, and then if we go one more layer in, we can look at the specific things that happened on that channel. So with that, I'm going to go ahead and skip back over to the capture tab, and I'm going to open up a packet capture called iPads.pcap. I really like this example. In this example, we went to a trade show, and there was an enterprise-grade wireless vendor that was streaming video to 100 iPads at the same time on an expo or trade show floor, which we thought was pretty cool. So we got a packet capture of that so we could see exactly what happened. Now, if we look at the innermost ring here, we can see that on this channel, we can see that we're on channel 52. So this is a 5 gigahertz channel. We can see that there's a total of 15 clients that talked to this access point, and we can see that our retry rate is about 24%. That's okay. That's not a great retry rate, but it's not terrible either, especially considering how toxic and noisy most trade show environments are. So we can see the iPad Demo 6 basically used up all of the airtime on this channel. Now, we had a little sliver of airtime used by another network called Voice WLAN 2 and another network called HP Blogger N, but it was almost insignificant amounts of airtime, almost no airtime used by that. Really, the network called iPad Demo 6 was really the one that used the most airtime. If we go one more layer out, we can see that there was one access point radio that was part of this network. And if we go one more layer out, now we can see how much airtime each of the Apple devices used up. I'm going to assume that that's probably the iPads, right? That's probably a pretty fair assumption, is that those are the iPads. Now, if we look up top here, this graph up here shows us how much airtime was used over time. So we can see that we hit about 100% airtime usage here. We can see that the airtime usage was peaked at 100%, and then it fell down a bit, and then it came back up, and then we had this big trough where we didn't use any airtime at all. Then we had a little burst again, and then we came to this point where we used tons and tons of airtime. So you can see how much airtime was being used over time. Now, I can click on any of these layers to drill down into them. So I'm going to click on the one of the Apple devices here to learn more about that. So we can see that this specific Apple device had a retry rate of 22%. Part of the time it was using a slow data rate like 6 megabits per second, but part of the time it was also able to hit a very fast data rate like 26 megabits per second. So if we look at the airtime chart here, we can see that it buffered some data right here, and that it buffered some more data later in the recording. If we back out and go look at a different iPad, we can see that it buffered its video data at a different point in time. So that's part of how this vendor was able to stream video to so many iPads at the same time. It kept them all buffering at different points in time, and you can really clearly see that by drilling down into them. Now, if we go to the Packets tab, this is going to give us kind of that Wireshark-esque view. This is all the packets that we saw on the network, and you can actually drill down into these to look at a specific conversation. You can either drill down using this pie chart here, or if you go to the Packets tab, there's kind of a mini pie chart over here in the corner that we can use. So if I click on that pie chart, Now we are looking at this specific Apple device, this one, and we can actually see those packets going back and forth. We can see that there are some retries here. These are all retries, but we can see those packets going back and forth. We could see that flow of packets where we had some quality of service data frames and then an acknowledgement and a request to send and a clear to send and then some data frames and another acknowledgement. You can see those packets back and forth, so you can actually see those conversations unfolding. Now, IEPA also has powerful filtering tools built in. It's all built in to the filters bar up here. We can filter down to a specific SSID. So if we want to filter down to just any SSID that has the name iPad, and I'm just going to type in iPad, and that's going to filter those other networks out. So now we're only looking at the iPad Demo 6 network. We can also filter down to a client vendor. So these are all Apple devices. So let's just filter down to Apple Incorporated, and that's going to filter down to only the Apple devices that are part of this network. And you can see those individual ones here. If we go to the Packets tab, this persists here as well. If we want to look at specific subframe types, like maybe we only want to show quality of service data frames, we can get rid of all the management frames, and we can get rid of all the control frames, and that's only going to leave our data frames, and we can actually uncheck these individually, and so now that's only going to leave us with quality of service data frames. And so IEPA is going to process that and apply that, and we'll be able to see only the quality of service data frames. Now let's say that we want to send a specific conversation to Wireshark. What we can do with that is I'm going to get rid of all these filters here, so let's just go get rid of all of those. And let's just get rid of everything and start over here. And then let's click on a specific Apple device and notice that that basically applies as a filter. So we are basically filtered down to this specific Apple device. And if we hit File and we hit Send to Wireshark, that's going to wrap up all these data frames and tie a bow on them, and it's going to open up all this data in Wireshark, so we can take a deeper dive into that specific conversation with Wireshark as well. Now, there's lots of other things I'd love to show you with this tool. I'd love to talk about the Analyze tab and how it will automatically, if you look at a specific network, this one's doing great, but if you look at a specific network, if there's something wrong with that network, it will automatically give you some recommendations. It will automatically call out devices that are talking too slow or talking too fast. I'd love to be able to show you that, but unfortunately, we've got to move on with the webinar. And so with that, let's go ahead and take some questions. If you have any questions about IEPA and packet analysis in general, feel free to use the question tool to ask those now. And also, we've got a gift for you here. We've got a free Wireshark color profile, and so you can apply this free Wireshark color profile to Wireshark, and it will give all the packets in Wireshark the same colors as the packet color assignments in IEPA. So with that, I'm going to go ahead and give it back over to Eva at Microcom.
Thank you very much for that wonderful presentation, Joel. It looks like we have a couple of questions. The first one is there any dead zones in which your product will not pick up a specific product?
I'm sorry, could you repeat that? I didn't quite understand it.
Is there any dead Is there any dead zones in which your product will not pick up a specific product?
So like a specific type of device. So with a packet analysis tool, you are only going to see 802.11 packets. So you are going to see 802.11 packets that conform to the 802.11 standard. If it's some kind of non-standard type of wireless transmission, you're not going to see that with a packet analyzer, but you should be able to see that with a spectrum analyzer, because a spectrum analyzer looks at the raw radio frequency activity.
Okay, the other one is there any marketing material I can use to send around to our team?
Yes, you can find some more information about this at MetaGeek.com, and if you have any sales questions, be sure to check with Microcom on that. But you can find more information about this tool at MetaGeek.com, whether that be on the product page for IPA or in our knowledge base.
Great. And then the last one, you said you run training courses. Can Microcom Technologies offer those courses as well through our Microcom Academy?
That's something that we'll have to discuss with Microcom. That may be something that we may be able to set up.
Great. So let's touch bases on that after. So I think that's it for questions. Thank you very much for answering those questions. Also, thank you everyone for attending today. If you have any questions, please feel free to contact your sales rep, or you can email us at sales@microcomtech.com. If you wish to view any of the products mentioned or shown today, please visit www.microcom.us or contact your sales rep as well. Please remember that the webinar presentation was recorded and it will be uploaded to our Microcom YouTube channel. So if you would like to reference it to again, you can view it on our YouTube channel. Thank you again and have a great day.